And with that, good morning, everybody. Welcome back to Calc 2 on this lovely morning, the day before spring break for most of us. Plan for today is we're going to wrap up Standard 8 by looking at a few more examples of arc length. I don't have any office hours for the next week or so.
What?
But I'll be in town. So, John, if you're here and you want to meet with me, send me an email to let me know. We'll figure something out. Okay.
All right, good.
As far as homework goes, don't forget you all have a homework set, homework 12. That's going to be due Monday after break, and a quiz on Standard 8. So, normally I would do a Standard 8 quiz on Monday in our next class because we're going to finish it up today. That being said, I know some of you might have strong feelings on doing a quiz at 7:45 a.m. the Monday right after spring break ends. So let's put it to a vote. Would you all rather do a quiz? Thank you. Would you all rather do a quiz Monday after spring break or Wednesday after spring break? Put it to a vote. All those in favor of Monday after break?
Not raising my hand now.
Devin, I'm subtracting your eventual vote. All those in favor of Wednesday after break? Okay, Wednesday it is. If you feel threatened by Devin, let me know. I'll smack some sense of them.
I do.
By constructing some extra nasty retests personally for him.
Oh.
Okay.
Sir, that is not permitted under the Union Convention.
I see no reason why not. Anyways, any questions or comments before we get started for today? Yes, Phoebe.
Can I have a Standard 8 packet?
Yes, you may. Anybody else? Quite a couple extras. So who needs a Standard 8 packet? Oh, now you can.
I think you just too early.
It was. Anybody else? Alrighty. So, what did the pirate say when he lost his parrot? He said, "Arr, Polygon." Polygon. Okay, so last time we talked about how to find compute arc length. So given some function f of x between 2 points a and b, we said that you could compute that arc length corresponded to, if you laid a piece of string or a rubber band, I didn't bring my rubber band today for effect, I'm sorry, over this curve and then kind of stretched it out tight, how long would that rubber band end up being? Which kind of gives us a way of computing the length of something that is curvy rather than just a straight distance like you're probably used to thinking about when it comes to looking at length. And we talked about how we could sort of do this definite integral and doing an infinite number of Pythagorean theorems to compute said length. And we said that the arc length of f of x from x equals a to x equals b was given by the integral from a to b of square root of 1 plus f prime of x quantity squared. And we looked at a couple of examples of actually putting that into practice. One with a line segment showing that just doing it with a straight line segment gives us the same answer as a single Pythagorean theorem, and one a little bit more messy. So what I want to do today is to talk through a couple more examples of putting arc length into practice. Specifically, you know how back in standard, what was it? That would have been standard 6, we proved that the area of the circle is pi r squared. We're going to do the same thing today, except we're going to prove that the perimeter of a circle is 2 pi r. So again, kind of using our calculus tricks here to prove a known formula from geometry, which I think kind of is interesting. So here's our goal. Prove perimeter of a circle of radius r is, when I say perimeter, I mean circumference, which is the same thing as perimeter, but just applied to circle rather than a typical polygon. That is Alright, so I want to look at the circle x squared plus y squared equals r squared. Taking some circle of radius r within the xy plane. So, how do you think we can use our arc length formula to find a formula for the perimeter, or perimeter, I mean to say circumference. Y'all got me thinking perimeter on the brain for some reason. How can we use our arc length formula to find the perimeter of this, to find the circumference of this circle? Sorry, I swear I'm not doing that on purpose. So one might think, hey, we have this sort of curve, it's a circle in the plane. We even have a formula for it. The problem is, it's not real. This isn't really a function. Y is a function of x, like the examples we did last time. Phoebe, what are your thoughts?
Could you find the arc length in the top right quadrant and then just add it 3 times?
Okay, so basically, and I think we did a similar sort of trick when we were finding the area of a circle a couple standards ago. Is you're going to say, well, trying to do the whole thing all at once is difficult, but circle is nice and symmetric. So if we were to say, just take the top right quadrant of the circle and, I don't know, multiply by 4, that should give us the whole thing. I like it. Yeah. So we're gonna have the same idea as last time. Instead of trying to do where last time, instead of trying to do the whole area all at once, we just did top right quarter of the circle multiplied by 4. We're gonna do something similar here. Just take the top right quarter. So our idea is you take the top right quarter of circle and multiply by 4. So what did we do last time to find a formula for y as a function of x for our top right quarter of the circle? James?
You could subtract the x squared over and then take the square root of both sides.
Okay, so we'll get y squared is r squared minus x squared, which is going to tell us what about y, James?
That it's equal to the square root of r squared minus x squared.
Yeah, it's going to be square root of r squared minus x squared. Do we need a plus or minus?
I think so. Or well, we're only dealing with the top right.
Yeah.
So,
Yeah, the fact that we're only dealing with the top right means I think we can just use the positive square root, which is why we kind of wanted to only deal with part of the circle in the first place, because if we wanted to do the whole thing at once, we would have y equals plus or minus square root of r squared minus x squared. In fact, I'll go ahead and write that in and then just circle the plus. But only doing the top of the circle means we only need to worry ourselves with the positive square root. So that can be our f of x formula, I think, for working through this process. So any questions or comments so far? All right, so then if we want to find the circumference of the circle, or at least of the top right quarter of the circle, we can use our arc length formula and take a 4 times some integral of 1 plus our f prime of x quantity squared. Joy, what would be the bounds on our integral? If we're just trying to do this top right quarter of the circle.
Between 0 and certain value.
Yeah, I agree. It is between 0 and a certain value. What is that certain value?
R?
Yeah, it's just going to go from 0 to r because this top right quarter of the circle starts at x equals 0 and ends at x equals r over here. So we're going to integrate from 0 to r the expression 1 plus, or square root of 1 plus f prime of x squared. And then if we multiply that by 4, that'll give us, ideally, the circumference of the entire circle rather than just the top right quarter. Okay. Gabe, what's going to be our f prime of x here? If f of x is the positive square root of r squared minus x squared, what would f prime of x be?
Square root of r squared minus x squared. Well, we have to differentiate.
Yeah, we have to differentiate first. All right. So if f prime of x is square root of, if f of x, excuse me, is square root of r squared minus x squared, keeping in mind that r is just a constant, Gabe, how would you go about differentiating that? Some chain rule. All right. What's that going to give us? My goodness, let's stomp it out there. I'm sorry, that was more interesting than whatever you were going to say. Yeah.
It's going to be 1 over 2 square root r squared minus x squared. Minus 2x.
Just
Well,
minus 2x?
times negative 2x.
Ah, times negative 2x. Yeah, which we can get from just using the chain rule on this expression. This is the same as r squared minus x squared to the 1/2 power. So differentiating the outside piece will give us 1/2 r squared minus x squared to the negative 1/2 power. But then we also have to multiply by the derivative of the inside piece. And keeping in mind that r is just a constant, the derivative of r squared minus x squared is going to be negative 2x. Which I think when we simplify, we'll give no, x doesn't cancel out, the 2 does. That's going to give us negative x over square root of r squared minus x squared. So we're going to have 1 plus negative x over square root of r squared minus x squared quantity squared plus 1 square root of all that integrated from 0 to r multiplied by 4. That sound good to you, Allie?
Yeah.
All right. Speaking of which, Allie, are we going to simplify what's under the square root? Or I guess what would you do first if you wanted to simplify?
Distribute the squared in
Okay, so what's that going to give us?
x squared over r squared minus x squared.
Yeah, it'll give us x squared over r squared minus x squared. Because if we square the numerator, the negative x times negative x will give us a positive x squared. Square root of r squared minus x squared, that's a lot of squares, will give us just r squared minus x squared. The square root and the square cancel out. Oh boy, holy moly. That looks terrifying. How can anybody have any ideas, bright ideas on how we might try and integrate this? Bethany, what's your idea?
Could we try to somehow factor the denominator of the last expression, or
Sure. Factor r squared minus x squared into r minus x times r plus x.
actually could we like combine like we did in the last problem, like we did in the problem last week where it was like for the circumference, like we could make 1 into r squared minus x squared and then combine the terms.
Okay. so basically combine this into a single expression, in other words, by rewriting one as a fraction and get a common denominator. Sounds good to me. Alright, if we do that, that'll give us square root of what? R squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared. And so, Bethany, what would that give us if we added our two fractions then?
It would give us r squared over r squared minus x squared.
Sounds good. Yeah, I think if we combine these, we would get r squared minus x squared plus x squared over r squared minus x squared. And so when we simplify a little bit, that'll give us square root of just plain old r squared over r squared minus x squared. Okay, that looks, I don't know, maybe a little bit easier to work with than 1 plus x squared over r squared minus x squared. So where can we go from here? Jonah?
Could you factor out the r squared and just like take it out of the integral?
I think so. Nora, did you have a question, or are you gonna give a suggestion?
Well, yeah, I was gonna say that, and it also looks a lot like an inverse trig value. So would that
That's interesting. Okay, yeah, we could split this up and say something like square root of r squared over r squared minus x squared is going to be square root of r squared over square root of r squared minus x squared. And then if we take square root of r squared, that's actually just going to give us, since we know r, since we're assuming r is a positive number here, it's the radius of our circle, r over square root of r squared minus x squared. And so Jonah, you propose that we take this r and just factor it out of the integral?
I think so.
Okay, I'm on board. Because r is just a constant, x is the kind of the variable here, r is just some constant referring to the radius of our circle. So that'll give us 4r integral from 0 to r of 1 over square root of r squared minus x squared. And Nora, what did you say that this looks like to you?
it looks like the inverse sine function.
Yeah, it looks a lot like an inverse sine function. In fact, this integral, I would say, is a type of integral that showed up on some standard 5 problems. All right, Nora, so how would you approach, or how do you think we should approach this one?
I think you could probably factor out an r from the expression, and then kind of.
From like the r squared minus x squared?
Yeah.
Okay. Yeah, I think we could do something like 4r integral 0 to r 1 over, what, square root of r squared, square root of 1 minus x squared over r squared? Factoring in r squared out of r squared minus x squared to leave us with r squared minus x squared is the same as square root of r squared times 1 minus x squared over r squared. Neato burrito. Okay, what can we do with that? James?
Oh, you can pull the square root of r squared out, which is just r, so it makes it 4r squared outside.
It is.
Or wait. Oh no. It just makes it a 4 outside.
And say, yeah, keep in mind this is in the denominator, so this we could actually write as 4r divided by r, integral 0 to r of 1 over square root of 1 minus x squared minus r squared. Man, my phone is buzzing. Someone's trying to reach me. And then we can, of course, do the old swoosh swoosh on these r's. Okay, so we have what, 4 times, oh hey, we're back to just 4 outside our integral again, times integral of 1 over square root of 1 minus x squared over r squared. Bethany?
Could we use u sub now and then like substitute substitute, make like u squared equal to x squared over r squared?
Ooh, sure. We could certainly do something like that. So, so what Bethany has proposed is, hey, we have 1 over square root of 1 minus blah. As Nora pointed out earlier, I think that looks an awful lot like an inverse sine derivative. So I agree. I think at this point it might make sense to try to do a little bit of a u sub. So you can either let u squared be equal to the x squared over r squared, or just let u be x over r. Comes out to the same thing. Keeping in mind that this expression right here is the same as just x over r quantity squared. So I think that would make du equal to what? Dx over r. So that r times du is equal to dx. Right. So in that case, we can rewrite this then, I think, as 4 times integral from x equals 0 to x equals r. Doing the James method here of just keeping track of the fact that 0 and r are x values, not u values, so we'll have to do some substitute x's back in later. And what are we going to end up with inside of our integral if we replace all of our x stuff with u stuff? Bethany?
So we could write it 1 over the square root of 1 minus u squared times all of that times r du.
Yeah. Replace the x squared over r squared with u squared, and replace dx with r times du. Oh hey, that r can go out in front. 4r integral from x equals 0 to x equals r of just 1 over square root of 1 minus u squared du. And Emerson, I think we're finally ready to integrate. What would we get if we tried to integrate 1 over square root of 1 minus u squared with respect to u?
It's the inverse sine of u, right?
It is indeed. We're going to get 4r times inverse sine of u. Or when we plug in our x expression back in for u, use the fact that u is equal to x over r, that'll give us 4r inverse sine of x over r, evaluated from r. By the way, I'd just like to point out that if we look at the constant multiples out in front of our integral, by the time we actually integrate it, we started with just 4. We then had 4r for a couple steps. Then we went back to just 4. Then we had 4r again for a couple of steps. That 4 out in front's going for a ride with r's. Any questions or comments about what we've done thus far? Alrighty, so now all that's left is to plug in our bounds, which will give us 4r inverse sine of r over r minus 4r inverse sine of 0 over r. Now, r over r just comes out to 1. Alright, I remember to give you all a cheat sheet. Oh, good, I did. So, what is inverse sine of 1 going to come out to? Okay? Yeah, pi over 2. If we're looking for, pulling out our unit circle for a second, if we look for the angle between negative pi over 2 and pi over 2 that has a sine of 1, that is a y value of 1 with its point on the unit circle, I think that's going to come out to pi over 2. How about inverse sine of 0? Bethany, what angle between negative pi over 2 and pi over 2 has a sine of 0? Huh, yeah, I think that'll just be plain old 0. That one's fairly straightforward. So what do we end up with? 4 pi r over 2, this 2 cancels out here with the 2, and wouldn't you know it? Turns out the circumference of that circle was in fact 2 pi r. Awesome possum lemon plus. It's nice when results like this come together. Some of you are probably thinking, Dr. Gerstle, I already knew the circumference of a circle is 2 pi r. Why did we have to do a bunch of head-splitting calculus in order to get that? Well, part of what mathematicians love to do is to take old results and try and prove them in different ways. So even though you may have already known that the circumference of a circle is 2 pi r from, say, previous math classes, I think it's worth spending the time to kind of go through some of our new methods and see, hey, we can even use our new methods to prove old results. To a true mathematician at heart, doing that sort of thing is cool. So if you thought that was cool, you may be a true mathematician at heart. If you thought that, oh my gosh, this is just a stupid exercise, I hate square roots, I hate inverse trig functions, I hate everything, then you're also probably a true mathematician at heart. Because we've all been there too. Any questions or comments about this? By the way, does anybody know the result in math that's probably been proved in the largest number of ways? I don't actually know this, but I think I know this. Pythagorean theorem has been proved in like hundreds of ways. People across history have always been trying to come up with new ways to prove Pythagorean theorem, c squared equals a squared plus b squared. Napoleon came up with a way. Garfield came up with a way. There's big names out there, some of which you wouldn't think have anything to do with math, that have come up with new ways to prove the Pythagorean theorem. Don't ask me how they proved it. I don't remember off the top of my head, by the way. If you want to talk about that, we can come to office hours and explore it together. Questions or comments? So really the bulk of standard 8 is working through this new formula, this square root of 1 plus f prime of x squared. Like once you actually set up this formula, once we got to like say this step, this is something I could have given you back in standard 5. It would have been mean of me to do so because this was a pretty involved process, which is why I wanted to work through it as a class. But deep down, this really does just come out to a standard 5 type question of, all right, we have square root of 1 plus f prime of x squared. What's our f prime of x? It was this, what expression Gabe came up with of negative x over root r squared minus x squared. Evaluate that out. And then depending on what you get under your square root, you may have to use one of our many different methods that we have available at this point for actually evaluating that integral. So in this case, hello outside. So in this case, according to Bethany's idea, we combine the expressions under the square root to get something like this. And then we use Nora's suggestion of, hey, that looks an awful lot like an inverse sine function. Let's try and integrate it with that approach in mind. Any questions, comments, concerns? All right. So, how are we doing? Doing great. Exercise time. Because, you know, it's the day before spring break. I can't just let you sit passively through class. It's not, you all got to do some math yourselves. So if you look at the next page of the packet, I give a couple of functions and a couple of intervals. So what I would like for you all to try and do, just for some practice, is working with your neighbors. See if you can find the arc length of the two functions I give you over the two intervals that I specified. So go ahead and, as always, take a few minutes, talk to your neighbors and/or flag me down if you have any questions, and see what you can make of these two expressions. I'll draw some graphs of them over here for you to look off of. Of course. That is Russian. No worries. Don't be shy about flagging me down if you and your neighbors get stuck somewhere. I don't know, just a fun fact about
Is it a hint at all?
figure maybe. It's not a hint for the first one, I'll tell you that. This is serious business, no giggling allowed.
Sorry, that's my fault.
I can't say that with a straight face, of course. This is all very silly stuff. And break's coming up. What's not to giggle about?
I'm already a giggly person, so there are so many giggles this way.
Fair enough. Hey, Gabe, what's up? I was agree, yeah. Answer doesn't always have to be a nice number. I'll give you, here's a hint. For the first one, do not expect the answer to come out to a nice number like 4 or something like that. Answer ends up being a little bit of a mess. Also, don't forget I gave you a trig sheet on the back for a reason.
No.
That bad.
Say what? Necessarily think so. That being said, I did not have
There might be
I don't think inverse tangent is a derivative of 1 plus. Inverse tangent is derivative of 1 over 1 plus thing squared. If it makes you feel better though, the actual answer doesn't have any trig. For that one at least. It was nice math for something that didn't apply. Fair enough. Hey, Lauren. Have you tried squaring out 3 halves that have 1 half?
It's not supposed to be 9, it's supposed to be 1 over 9. Put it back. Because there isn't a 9. Oh, I'm, yeah. So it's, yeah, it's so it'd be 180.
So what would you get you to x to the 1 half times x to the 1 half?
And then if I want
And what happens if you multiply out 3 halves times 3 halves? What fraction is that?
I would simplify it. Well, but then it would still be.
like I'm simplifying it before I flip that. So if I like flip this upside down, I'll just like multiply it by top bottom. Then that would cancel out to then 2/3 u and multiply that by 8 times 3.
9.7. 1 plus 9.7. And then I would suggest trying to use some of that expression. You try letting them use 1 plus 9.7 and see if that can help you. I'll let you think about that.
Oh
What's
god,
up,
I
Gabe?
need to subtract.
I don't see why not. Square root of 1 plus tangent squared x. Well, technically, it would be 1 plus the quantity negative tangent x quantity squared. But negative tangent x, when you square it, would just give you a positive tangent squared. Ends up having to, only because the negatives end up being
You gotta plug your U, you gotta plug it back to this. Oh, you write your own U.
My D, okay, upstairs 18.
Alright, how are things going back here?
Think so far so good. Maybe
Groovy.
we'll see.
That would be even groovier.
302. The power is that you're taking square root of it and then cubing it. Yeah.
Oh.
Or the other way around. Like
What happened to your 3 halves?
yeah. I don't think it matters. Well, when you do.
Oh.
I say that's why the answer I got wasn't so nice. But I think that is what I got after at that
Okay,
step at
after
least.
that step.
I don't remember what my final answer was, but just whatever you get when you plug in 1 and 2 for that expression. How's it going, Deb? So you took that. Where did the 1/2 x negative 1/2? Oh, you did a U sub. Gotcha. So, I like your idea of using a U sub.
I think it just.
I think you want a different U than what you did. I'll give you a hint. What I did for my U is I let U be everything under the square root.
Okay.
And then that ended up being a more useful U for me at least to work with. Because otherwise I think you're just going to get a big mess under the square root. No way to really deal with it.
Yeah, I think it just ends up being stuff.
Gotcha.
What do you do?
Hey, enjoy.
302.
I see.
I'm just leaving it as like 3 halves.
Did this a little differently than how I did it, but this way it works. 1/2 square root of U, so 20. So that's 20 times 1/3. Where it comes out 27.
Like over this.
I think that's the right idea.
Okay.
I did it slightly differently. I did a slightly different use of than what you did, so my answer looks a little different from yours, but I think it may come out to the same thing.
Dr. Gerstle, what's the final answer? Is that right?
Hey, that's what I got as,
Cool.
well, approximately correct answer.
Sounds good.
Dr. Crystal, is that what you got?
Oh, I didn't divide it.
It is indeed. Nice job.
So, yeah, so then we can square root, you can take it. This, like, it's this part, so you don't see nothing. So I put 9x plus 4 on top, all over here. Oh, wait. And then I squared it.
Oh, I see.
Yeah, so
Cosine squared here.
Um,
The integral of 1 over cosine squared, or square root of that is.
yeah,
Well, you can split it up like that, but I just don't think you can evaluate it like that.
and then I just have these
I'll give you a hint.
Oh, so this is.
I was able to rewrite this as
So now
1
you-
over
and now you
secant,
like-
1 over cosine of x. Once you do each square root, you just get secant of x in the integral. And then, wrote a hint up on the front board there. It's a little hard to see from your perch on how we might integrate that. Over on that side. Here, I'll write the hint at the front
And
of
then
the
you
room.
plug it in. And then everything
What?
else is the same as normal use of. So do you want each piece, because you have to divide by this. And you divide one. So do you want to divide one? And then you do one.
That's fine. That's true. What's up?
Do you do a use of square root multiplication by parts to get that?
To get that?
1/2.
Yeah. Well, yeah, that would be how you could do it backwards. Technically, if you wanted to integrate secant
Yeah,
x,
so now you're left with 180 times 2/3 due to
the easiest way to actually integrate this is to do something what I would call very unintuitive.
2/3 times.
We're gonna multiply by
Let's simplify it.
secant x plus tangent x over secant x plus tangent x,
2.08.
Yep.
which if you evaluate that out will come out to secant squared x plus secant x tangent x over
You get 127 for
the
the
secant x plus tangent x,
So it would be 2 over.
and then you can do a u sub.
But
Bruh.
250.
Alright, Gabe, oh no, now you got me started, now I have to
That's
add.
almost like 1/8.
What would be your u in this expression?
180 times 2 like simplifies down to 27.
Unless it says on the whole, like, walking.
It's 254.
Turns out,
Why do you do that? Well, you know,
I think secant x plus tangent x would be your u. Because if u is equal to secant x plus tangent x, what would that get you for your
I thought it
du?
was, ask James actually, James, what do you do with that?
Not just secant x.
That's a log of this.
Well, first of all, what's the derivative of secant?
And then
Oh,
plug it back in.
It's the very first step of the second.
Yeah. I thought the derivative of secant x
It is, yeah, that's secant x.
Yeah, so
What's that plus?
So.
Oh, yeah, okay.
Derivative of
Tangent.
Whatever goes sometimes, sine of x.
he did it.
Negative
Oh, hey, so look at that.
It's just, yeah.
That just turns into 1 over u when you integrate it. And then you get natural log absolute value of u, which gives you the natural log absolute value of secant x plus tangent x. But yeah, the real trick under this one is how would you know to multiply by that in the first place? And I don't really have a good intuitive answer for why you would try to do it that way. It just, that's just a sort of known trick in calculus that happens to work out.
It's just like tangent derivative.
Alternatively, you could just differentiate. You could look into your crystal ball and say, maybe I should try natural log of absolute value of secant x plus tangent x, differentiate it, simplify the derivative down to just secant x and say, oh hey,
Oh, you mean like.
turns out that works, so you can integrate going backwards. What do you know?
The where it's like secant squared plus tangent squared plus.
Oh. Yeah.
So
So
then
What's natural log of one?
we have Dr. Mercer that did this early in the morning.
It is, for a class you signed up for that meets 3 days a week at this time in the morning.
And I'm really used to it. It is 0, which is,
There you go.
wait, it would be.
it's just early for the Friday before we all leave, you know?
You know, I can respect that. Yeah, this may shock you, but I'm feeling it myself. Hey, dude.
So,
Oh, wait, I think I got it.
and then are we gonna somehow do?
Yeah.
I wanna
Hold on,
keep
I
this
got
like,
it.
I think I got-
my
wait,
answer,
you need to
so
go
I
back.
find it slightly clean way, it's not quite the first time.
I don't,
So,
It's just a bunch of square roots.
yeah, it's very sure.
oh, for g prime of x,
Yeah.
don't use the head. Get to it later when you're actually integrating.
Oh,
I think for differentiating g of x, you just want to try using the chain rule on that.
Does that have that? If I, it's more simplifying?
It doesn't end up coming out to secant x.
I don't know.
Let's go to some
Oh, and
others.
then also,
Well, wait a second.
So the second one's hard, the first one, oh, whatever it is.
I think I might have just thought
I don't
the
know.
way
I don't
to
even know.
simplify it better.
So,
cause it's like a negative if you bring it up.
yeah, so basically, this is the right idea.
That's correct, okay, I wasn't sure that was just wrong. So, cause e to the x, the control of that is just e to the x.
Correct.
So if it's a negative x, then it's negative.
Yep. You can get from doing like a quick u sub or just
Okay.
knowing that if you have that negative, it's gonna have another negative factor out in front.
Okay. Thank you.
It's negative 14.
Let's go take about 1 more minute, then we'll come back together and talk a little bit as a class.
Jake, is there natural law?
Doing all right, Nate?
Oh,
I was gonna say, a lot of racing. So.
wait, hold on, sorry, it's tangent.
Doing all right, Nate? Yeah. Cool.
Yeah, so this is the derivative of the whole thing, times the derivative of the inside. I just simplified it. No derivative of cosine. Well, derivative of natural log of cosine x is 1 over cosine x. Because it would be like 1 over x, like it's 1 over the inside piece is the derivative.
Spoken like a true.
Yes. Okay, yeah. And derivative of natural log of x, 1 over x. Yeah, okay.
Let's say I got something like 2.0 now.
So it's negative tangent.
So I agree with that. So I agree with your integral. Oh, good. Yeah, sorry. Sorry, it's down here. 827 times 1. Yeah. 27 so I agree with your. I still agree with your integral.
Yeah.
I'm guessing you just
The
plug something
negative
in.
tangent gets squared, then it's
Good.
yeah. Positive tangent is squared.
I got 827 times.
Which I think you can do.
Oh, keep in mind 827, you can't pull that inside with 3 halves. Because 8, unless you wanted to take 827 to the 3 halves power itself first.
I know.
Or to the 2 thirds power, basically.
That makes sense.
It's close to what I've got.
Oh, now we can use this.
I'm gonna come around.
Yeah, you're right. That would just get you.
Let's see, zero
Okay,
in.
says.
Would that cancel out?
I think so.
Secant pi
Cause
over
it's the only
3.
thing. So now we gotta get.
I think secant pi over
Hold on, I got you.
Me too. It's like looking at it, I
Oh,
was
shit.
like, wasn't quite sure. I was like,
secant pi over 3 is 1 over
Oh,
cosine pi
natural
over
log
3,
secant.
cosine of pi over 3 is square root of 3
Natural
2,
log
so you got
secant x plus
3. Tangent of pi over 3.
What did you choose?
That's the derivative of cosine.
Tangent of pi over 3.
Y is.
Tangent pi over 3. I think secant of pi over 3 comes out to.
Oh, that's why. It's the end of the.
Okay, so you said cosine is. I think you're looking at pi over 6. Because if you look at pi over 3 actually has a cosine of 1/2 the sine of square root over 2, not the other way around.
No.
That tripped me up just now trying to look at.
Oh,
and it's,
yeah.
Trickle get.
You just messed up basic calculation. This part right here is gonna have second x 1/2 squared.
Can we catch
Alrighty, let's come back together for a minute. So I think we have time to talk about one of these 2 problems as a class. So let's put a vote on which problem we work out together. Who would rather see the x to the 3 halves example? 1, 2, 3, 4, 5, 6. Who would rather 7? Who would rather see the natural log cosine of x example? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Somewhat narrow vote compared to how this class usually goes, but this one I think was the winner. I'll be posting my solutions after class day so you can see what I did for both of the problems either way. So let's start with natural log of cosine of x. So if we have g of x equals natural log of cosine of x, our arc length is going to end up being integral from 0 to pi over 3 square root of 1 plus g prime of x squared, same as usual. But I guess we're calling our function g instead of f. Maybe that's not usual to you. How do we differentiate natural log of cosine of x? Okay.
So you do derivative of outside times derivative of inside, so.
Derivative of outside times derivative of inside.
I don't know, it's chain rule, I don't know.
It's chain rule, what do you want from me? Alright, so what's it gonna give us here?
Like derivative of natural log is 1 over x, so you have 1 over cosine x times derivative of cosine, which is minus sine x. So it's negative tangent.
And we end up with negative sine of x over cosine of x when we do our chain rule, which just comes out to negative tangent of x. And if we plug that in here, we'll get integral from 0 to pi over 3 of square root of 1 plus, what? That's just going to be tangent squared x. Because when we square negative tangent of x, the negative cancels out. How are we going to deal with this mess? Square root of 1 plus tangent squared x. Steve?
Well, there's like that trig property thing where 1 plus square tangent squared is secant squared.
Oh, there is that trig property thing. Yeah. Didn't you know it? 1 plus tangent squared is equal to secant squared. That's a Pythagorean identity. That's what you get if you take sine squared plus cosine squared x equals 1 and divide both sides of that equation by cosine squared x. Okay. How are we going to simplify, Rodum, square root of secant squared x?
It just becomes secant x.
Oh goodness, how do we integrate secant of x? Phoebe, any ideas?
We use the hint on the board.
Holy moly, we use the hint on the board. By the way, if you don't know where does that hint come from, because this is one, I think we've used this like once before, but it's been a while. The way you can actually integrate secant of x is you can do something very unintuitive. Multiply by secant x plus tangent x over secant x plus tangent x, which ends up giving you integral of secant squared x plus secant x tangent x over secant x plus tangent x. And then we're going to do a use of, where u is equal to secant x plus tangent x. Just so happens if you do that use of, you end up with just integral of 1 over u with respect to u, which comes out to natural log of absolute value of u, which is natural log absolute value of secant x plus tangent x. Yeah, so using our hint, we end up with natural log, absolute value, tangent x plus secant x from 0 to pi over 3. I think I just wrote it backwards of how I originally wrote it, but I'm sticking with it. Which is what? Natural log, absolute value of tangent of pi over 3 plus secant pi over 3 minus natural log of tangent of 0 plus secant 0. All right. Bethany, what's tangent of pi over 3?
Tangent of pi over 3 is, tangent of pi over 3 is square root of 3.
Yeah, it's going to be square root of 3 halves divided by 1 half, which simplifies to square root of 3. What's secant of pi over 3? One that was given up, both of us fits earlier.
2.
Yeah, cosine of pi over 3 is 1 half. So secant of pi over 3 is 1 over a half, or 2. Emerson, what's tangent of 0?
Tangent of 0 is tangent of 0 is sine of 0 or cosine of 0, which is 0 over 1, which is 0.
And secant of 0?
Secant of 0 is 1 over cosine of 0, which is 1.
1 over 1, so 1. Alright, so we end up with natural log of, well, this is positive, so I don't need the absolute value anymore. Hey James, what's natural log of 1?
0 over 1.
That's a weird way of saying 0, but yep. That's what I got for my answer to this one. Natural log of root 3 plus 2. So, when we come back, we're going to get into some theology and talk about the Archangel Gabriel. Namesake of our own, Gabriel the Rose. And what we're going to do is we're going to look at his horn and talk about how when you're an archangel, that gives you powers of being able to have carry a horn with you that has an infinite surface area to it. And yet, somehow it will only have a finite volume. Go figure. Maybe you're going to have to explain that to me sometime. We'll talk about that after the break. Have a good spring break, everybody. Safe travels. See y'all in a week. Hope you all have a chance to relax, etc. We'll do the quiz the Wednesday after break, so you don't have to come right back to quiz time. Have a good one.